Welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reed, and tonight we're embarking on a journey to one of the most mysterious and misunderstood worlds in our solar system. Venus, Earth's twin sister. A planet that appears as a brilliant jewel in our evening and morning skies, yet harbors one of the most hostile environments we've ever discovered. Tonight, we'll travel from the crushing clouds of sulfuric acid that shroud this world to the volcanic plains that stretch across its surface. We'll explore why Venus became a hothouse while Earth flourished with life. We'll discuss the strange backwards rotation of this planet and the mysteries that still puzzle scientists today. We'll examine the possibility that Venus may have once been a very different place, perhaps even a world with oceans. And we'll look at the missions that have braved this inferno to send back precious data about our neighboring planet. If you enjoy these types of videos where we explore the cosmos together in a calm and thoughtful way, please consider giving this video a thumbs up and subscribing to the channel. It helps more people discover these astronomical journeys. I'm also curious, where in the world are you watching from right now? And what time is it where you are? Drop a comment below. I love hearing from fellow space enthusiasts around the globe. Let's dive in. Venus has captivated humanity for thousands of years. Ancient civilizations tracked its movements across the sky with remarkable precision. The Maya calculated the Venus cycle to within hours over centuries of observation. The Babylonians kept detailed astronomical diaries that tracked Venus alongside the Moon and other planets. To the naked eye, Venus outshines every celestial object except the Sun and Moon. This brilliance comes from Venus's thick atmosphere and its proximity to Earth. At its closest approach, Venus comes within about 38 million kilometers of our planet, closer than any other planet in the solar system. The clouds that envelope Venus reflect about 75% of the sunlight that reaches it, making it extraordinarily bright. This reflectivity, called albedo, is higher than any other planet. For much of human history, people didn't realize that the morning star and evening star were the same object. The ancient Greeks initially called the morning appearance Phosphorus and the evening appearance Hesperus. Eventually, they recognized these were a single wandering star, which they named Aphrodite. The Romans later renamed it Venus, after their goddess of love and beauty. The planet's beauty from afar stands in stark contrast to its actual nature. Venus is almost exactly the same size as Earth, with a diameter of about 12,100 kilometers compared to Earth's 12,742 kilometers. It has about 82% of Earth's mass. This similarity in size and composition is why Venus earned the nickname Earth's twin. But that's where the similarities end. Venus orbits the Sun at an average distance of about 108 million kilometers, roughly 72% of Earth's distance from the Sun. It completes one orbit every 224.7 Earth days. But here's where things get strange. Venus rotates on its axis incredibly slowly, taking about 243 Earth days to complete one rotation. This means a day on Venus is actually longer than its year. Even more peculiar, Venus rotates backwards compared to most planets in our solar system. While Earth and most other planets rotate counterclockwise when viewed from above the North Pole, Venus rotates clockwise. This retrograde rotation remains something of a mystery. Scientists theorize that a massive collision early in Venus's history might have flipped it over, or that gravitational interactions with the Sun over billions of years gradually reversed its spin. The slow rotation has profound effects on Venus's environment. On Earth, our relatively rapid rotation helps generate our magnetic field through the dynamo effect in our planet's molten core. Venus, rotating so slowly, generates no significant magnetic field. This leaves the planet vulnerable to the solar wind, the stream of charged particles flowing from the sun. Without a magnetic shield, the solar atmosphere directly interacts with Venus's upper atmosphere, slowly stripping it away into space. From our perspective on Earth, Venus never strays far from the sun in the sky. It reaches a maximum elongation, or angular distance from the sun, of about 47 degrees. This means we can only see Venus in the hours around sunrise or sunset. For ancient observers, this dance with the sun added to Venus's mystique and importance in various mythologies and early astronomical systems. The atmosphere of Venus is one of the most extreme environments in our solar system. Standing on the surface of Venus, you would experience atmospheric pressure 92 times greater than Earth's sea level pressure. To put this in perspective, this is equivalent to the pressure you'd feel if you dove about 900 meters beneath Earth's oceans. The weight of all that atmosphere pressing down would be immediately noticeable. This crushing atmosphere consists of about 96.5% carbon dioxide. The remaining few percent includes nitrogen and trace amounts of other gases. The density of this atmosphere is about 67 times that of Earth's atmosphere. If you could somehow survive on Venus's surface, moving through this atmosphere would feel more like wading through water than walking through air. The temperature at the surface averages about 467 degrees Celsius, or 873 degrees Fahrenheit. This is hot enough to melt lead, which melts at 327 degrees Celsius. Remarkably, this temperature remains nearly constant across the entire planet. The equator and the poles, the day side and the night side, all maintain this hellish temperature. The thick atmosphere acts like a blanket, redistributing heat so efficiently that temperature variations are minimal. This extreme greenhouse effect is what makes Venus so incredibly hot. Although Venus receives only about twice the sunlight that Earth does, its temperature is far higher than Mercury's, despite Mercury being much closer to the sun. The carbon dioxide traps infrared radiation trying to escape from the surface, causing temperatures to build up over time. It's like parking a car in the sun with the windows rolled up, except on a planetary scale and far more extreme. The clouds of Venus form a permanent layer about 45 to 70 kilometers above the surface. These aren't water clouds like Earth's. They're composed primarily of sulfuric acid droplets. Sulfuric acid is the same corrosive substance used in car batteries. These clouds are so thick and extensive that they completely hide the surface from view. No telescope from Earth or even from orbit around Venus can see through these clouds using visible light. These sulfur compounds likely come from volcanic activity on Venus's surface. When sulfur dioxide is released by volcanoes, it rises into the atmosphere where ultraviolet light from the sun breaks it apart and allows it to combine with water vapor, forming sulfuric acid. The acid droplets form clouds that eventually produce rain. However, this rain never reaches the surface. The intense heat in the lower atmosphere causes the sulfuric acid raindrops to evaporate long before they could fall to the ground. The atmosphere displays another fascinating feature. The clouds race around the planet in just 4 Earth days, even though the solid planet below rotates once every 243 days. This phenomenon, called superrotation, means the atmosphere moves about 60 times faster than the planet's surface. Imagine if Earth's winds constantly blew at over 400 kilometers per hour. Scientists are still working to fully understand what drives this superrotation. High-altitude winds on Venus reach speeds of about 350 kilometers per hour near the equator. These winds decrease with altitude. At the surface, winds are sluggish, moving at only a few kilometers per hour. The thick atmosphere and slow rotation create a very different weather pattern than Earth's. While Earth has complex systems with high and low pressure areas that move around, Venus's weather is dominated by these high-altitude winds circling the planet. For centuries, the surface of Venus remained a complete mystery, hidden beneath its impenetrable cloud deck. Early science fiction writers imagined Venus as a world of steamy jungles and perhaps even dinosaurs, assuming that more sunlight would create a warmer, wetter version of Earth. The reality turned out to be far different and far more alien. Our first glimpses of Venus's surface came from Soviet Venera landers in the 1970s and early 1980s. These spacecraft provided the first and still the only photographs taken from the surface of Venus. The images showed a rocky, barren landscape bathed in an orange glow from sunlight filtering through the clouds. Flat stones and rocks scattered across the surface suggested volcanic activity. The landers survived only briefly, from about 23 minutes to just over 2 hours, before succumbing to the extreme heat and pressure. Later, radar mapping from NASA's Magellan spacecraft in the early 1990s revealed Venus's surface in unprecedented detail. Radar can penetrate the clouds, bouncing off the surface below and creating detailed maps. What these maps showed was a world dominated by volcanic features. About 80% of Venus's surface consists of volcanic plains, smooth areas formed by lava flows. Venus has tens of thousands of volcanoes, far more than Earth. Most are shield volcanoes, broad, gentle slopes similar to those found in Hawaii. Some of these shield volcanoes are enormous. Mont Mons, the tallest volcano on Venus, rises about 8 kilometers above the surrounding plains. While not as tall as Mars's Olympus Mons, it's still taller than any mountain in the lower 48 United States. Venus also features unique volcanic structures not found on Earth. Pancake domes are circular, flat-topped features formed when thick, viscous lava oozes out and spreads into a circular shape before hardening. Some of these pancake domes measure up to 65 kilometers across. Another unique feature is arachnoids, circular to elongated structures with radial patterns that resemble spiders. These may form when magma rising from below pushes up the surface, creating fractures that radiate outward. Coronae are perhaps the most distinctive features on Venus. These are large circular structures, ranging from 150 to over 2,000 kilometers in diameter, surrounded by concentric ridges and troughs. Scientists believe coronae form when plumes of hot material rise from deep within Venus's mantle, pushing up the surface. As the plume spreads out beneath the crust, it creates these circular patterns. Over 500 coronae have been identified on Venus. The question of whether Venus is still volcanically active remains open. Several pieces of evidence suggest ongoing volcanism. Variations in sulfur dioxide levels in the atmosphere over time could indicate volcanic eruptions releasing fresh gas. Some surface features appear too fresh to be ancient, lacking the weathering and impact craters you'd expect on very old surfaces. Recent analysis has suggested possible active lava flows, though this remains debated. Venus has relatively few impact craters compared to Mercury, Mars, or the Moon. Scientists have identified fewer than 1,000 craters on Venus. This suggests the surface is relatively young in geological terms, perhaps only 300 to 500 million years old. Something resurfaced most of Venus in the relatively recent past. This could have been a period of intense volcanic activity that covered older surfaces with fresh lava. The distribution of craters is remarkably uniform across Venus. Unlike Earth, where plate tectonics creates areas of different ages, Venus's craters are spread evenly. This suggests the resurfacing event or events affected the entire planet rather than occurring in stages across different regions. Understanding this resurfacing remains one of the major questions in Venus science. One of the most profound questions about Venus concerns water. Today, Venus is the driest known planet in our solar system. The atmosphere contains only about 30 parts per million of water vapor, compared to Earth's atmosphere, which averages about 10,000 parts per million. The entire planet has less water than exists in just a small section of one of Earth's oceans. But Venus wasn't always this way. Scientists have found compelling evidence that Venus once had significantly more water, possibly even oceans covering much of its surface. This evidence comes from studying the ratio of different hydrogen isotopes in Venus's atmosphere. Hydrogen comes in different forms, or isotopes. Regular hydrogen has just one proton in its nucleus. Deuterium, sometimes called heavy hydrogen, has one proton and one neutron. On Venus, the ratio of deuterium to regular hydrogen is about 150 times higher than on Earth. This enrichment in deuterium tells a story of loss. Water molecules containing regular hydrogen are lighter and can more easily escape into space when they reach the upper atmosphere. Water molecules containing deuterium are heavier and more likely to remain. Over billions of years, as Venus lost its water to space, the ratio of deuterium to hydrogen increased dramatically. By working backwards from this ratio, scientists estimate that Venus may have once had enough water to cover the planet in an ocean about 25 meters deep. Some models suggest even more water, enough for a global ocean 300 meters deep or even deeper. While this is far less than Earth's oceans, which average about 3,700 meters deep, it would have been enough to dramatically change Venus's environment. What happened to Venus's water? The story begins with the Sun. In its early history, the Sun was about 30% dimmer than today. As the Sun aged and fusion in its core became more efficient, it grew brighter. This increasing solar output gradually heated both Earth and Venus. Earth, being farther from the Sun, warmed to pleasant temperatures that allowed liquid water to persist. Venus, being closer, crossed a critical threshold. As Venus warmed, more water evaporated into the atmosphere. Water vapor is itself a greenhouse gas, trapping heat. This created a runaway greenhouse effect. More heat caused more evaporation, which trapped more heat, which caused more evaporation. Eventually, temperatures climbed so high that the oceans completely evaporated. Venus entered what scientists call a moist greenhouse state, with the atmosphere full of water vapor. In the upper atmosphere, ultraviolet radiation from the Sun broke apart water molecules through a process called photodissociation. The oxygen atoms combined with other elements in rocks and the atmosphere, getting locked away. The hydrogen atoms, being very light, escaped into space. Without a magnetic field to protect it, Venus's atmosphere was vulnerable to the solar wind, which helped strip away the hydrogen. This process took hundreds of millions or even billions of years, but eventually Venus lost most of its water. The carbon dioxide that had been dissolved in the oceans was released into the atmosphere. Volcanic activity continued to add more carbon dioxide. Without water or life to recycle carbon dioxide like Earth's ocean and plants do, the carbon dioxide accumulated, creating the thick atmosphere we see today. The timing of Venus's water loss remains debated. Some scientists think Venus lost its water very early in its history, perhaps within the first billion years. Others think Venus might have retained water much longer, possibly until 2 billion years ago or even more recently. The answer has profound implications for whether Venus could have supported life during its wetter phase. Understanding Venus's transformation from a potentially habitable world to the hothouse we see today helps us understand Earth's climate and the search for life on planets around other stars. The climate of Venus represents one of the most extreme transformations possible for a terrestrial planet. While Earth and Venus likely started with similar conditions, they diverged into radically different worlds. Understanding how and why this happened helps us appreciate both the fragility and resilience of planetary climates. The greenhouse effect on Venus operates on a scale difficult to fully grasp. Greenhouse gases in an atmosphere allow visible light from the sun to pass through but trap infrared radiation trying to escape back into space. On Earth, this natural greenhouse effect warms our planet by about 33 degrees Celsius, making it habitable. Without it, Earth's average temperature would be well below freezing. On Venus, the greenhouse effect adds about 500 degrees Celsius to the surface temperature. Think of Venus's atmosphere as a tremendously thick blanket wrapped around the planet. Sunlight penetrates the clouds, though only about 25% reaches the surface. This light warms the rocks, which then emit infrared radiation. But this infrared radiation can't escape. The carbon dioxide molecules absorb it, heating the atmosphere. The hot atmosphere radiates energy both up and down, warming the surface even more. The clouds add another layer of complexity. Sulfuric acid droplets in the clouds reflect most incoming sunlight back into space, which actually keeps Venus cooler than it would otherwise be. Without these reflective clouds, Venus would be even hotter. The clouds also scatter light, creating the eerie orange glow visible in images from the surface. At the surface, the thick atmosphere scatters so much light that there are no sharp shadows. The illumination is diffuse and even, like an overcast day on Earth, but far more extreme. Temperature variations on Venus are remarkably small. The equator and poles differ by only a few degrees. Day and night are virtually identical in temperature. This happens because the thick atmosphere redistributes heat so efficiently. It would take an enormous amount of energy to cool any part of Venus's surface, more than can be lost during its long night. The heat capacity of the atmosphere, its ability to store thermal energy, combined with circulation patterns, ensures temperatures remain constant. Atmospheric circulation on Venus differs dramatically from Earth. On Earth, the temperature difference between equator and poles drives large-scale circulation patterns. Hot air rises at the equator, travels toward the poles at high altitude, sinks at the poles, and returns toward the equator at low altitude. These Hadley cells, as they're called, organize Earth's climate into zones. Venus has a single Hadley cell in each hemisphere. Air heated at low latitudes rises, travels toward the poles at high altitude, sinks at the poles, and returns toward the equator at lower altitude. But because temperature differences are so small, this circulation is driven more by the slow rotation and heating patterns than by temperature gradients. The super-rotating winds, moving much faster than the planet itself, dominate the circulation. At the poles, Venus displays a remarkable feature called a polar vortex. Similar to but more pronounced than Earth's polar vortices, Venus's polar vortex creates a strange double-eye pattern when viewed from above. The atmospheric circulation spirals down toward the pole, creating swirling clouds in a pattern that resembles a hurricane. The temperature at Venus's poles is actually slightly higher than at the equator, opposite to what we see on Earth, because descending air compresses and warms. The lower atmosphere is relatively calm. At the surface, Winds blow at only about a meter per second, slower than a leisurely walk. The air is so dense that even these slow winds exert significant force, similar to ocean currents on Earth. Visibility at the surface would be limited to a few hundred meters by the thick, hazy atmosphere. Exploring Venus has proven to be one of the most difficult challenges in planetary science. The combination of crushing pressure, corrosive atmosphere, and extreme heat destroys conventional spacecraft within hours. Despite these challenges, humanity has sent dozens of missions to Venus, achieving remarkable successes and gaining invaluable insights into our sister planet. The Soviet Union's Venera program remains the most successful series of Venus landers. Between 1961 and 1984, the Soviets launched multiple missions to Venus. The early missions failed or provided only limited data, but gradually Soviet engineers developed techniques to survive Venus's environment. They built spacecraft with thick pressure vessels, cooling systems, and reinforced electronics. Venera 7 became the first spacecraft to successfully transmit data from the surface of another planet when it landed on December 15, 1970. It survived for 23 minutes before succumbing to the heat. Venera 7 confirmed the extreme surface temperature and pressure that scientists had suspected but not yet proven. This was a monumental achievement in space exploration. Later Venera missions improved on this success. Venera 9 and 10, which landed in 1975, carried cameras and returned the first black and white images from Venus's surface. The images showed a rocky surface with flat stones, suggesting volcanic activity. Venera 13 and 14 landed in 1982 and returned the first color images. These showed an orange-tinted landscape with scattered rocks and what appeared to be volcanic soil. These Soviet landers also analyzed the soil composition using X-ray fluorescence spectrometers. The results showed that Venus's rocks are similar to volcanic basalt found on Earth, confirming that Venus is geologically similar to our planet in composition. Some landers also detected possible lightning during their descent, though this remains controversial and debated among scientists. NASA's Pioneer Venus mission arrived in 1978 and consisted of an orbiter and multiple atmospheric probes. The orbiter mapped the surface using radar, providing the first global view of Venus's topography. The atmospheric probes measured the composition, temperature, and pressure at different altitudes and locations. These missions revealed details about the cloud layers and the extreme greenhouse effect. The most detailed mapping of Venus came from NASA's Magellan spacecraft, which orbited Venus from 1990 to 1994. Using synthetic aperture radar, Magellan mapped 98% of Venus's surface with a resolution better than 100 meters in most places. The data revealed the extensive volcanic features, the coronae, the impact craters, and the relatively young surface age. Magellan's maps remain the primary source of information about Venus's topography. European Space Agency's Venus Express orbited the planet from 2006 to 2014, studying the atmosphere in detail. Venus Express discovered the unusual double vortex at the South Pole and tracked changes in atmospheric composition over time. The spacecraft detected a possible sign of active volcanism when sulfur dioxide levels increased temporarily, though this interpretation remains debated. Japan's Akatsuki orbiter, which entered orbit around Venus in 2015 after a failed first attempt, continues to study Venus's atmosphere and weather patterns. Akatsuki has revealed details about the superrotation and discovered planetary scale waves in the atmosphere. These waves ripple through the cloud tops, possibly influenced by surface topography. More missions are planned for the coming decade. NASA has selected 2 missions to Venus. Veritas will create high-resolution topographic maps and search for active volcanism. Da Vinci will send a probe through the atmosphere, analyzing composition and taking pictures during descent. European Space Agency has approved Envision, another orbiter that will study Venus's surface and interior. These missions, planned for launch in the late 2020s and early 2030s, will answer many outstanding questions about Venus. One of the most intriguing questions about Venus concerns its distant past. Could Venus have once been habitable? Could it have supported life? These questions have moved from speculation to serious scientific investigation as our understanding of Venus has deepened. Several billion years ago, conditions on Venus were likely very different. The young sun was dimmer, providing less heat. If Venus had water oceans at this time, the planet might have maintained temperatures suitable for liquid water at the surface. Climate models suggest that Venus could have remained habitable for as long as 2 or 3 billion years after its formation, perhaps even longer. For Venus to have been habitable, several conditions would need to have been met. First, it would need liquid water at the surface. Second, temperatures would need to stay within the range where biochemistry as we understand it could function, roughly between 0 and 120 degrees Celsius. Third, the atmosphere would need to be much less dense and hot than today. Could Venus have maintained these conditions? Some climate models say yes. If early Venus had enough water, and if clouds formed over the oceans, these clouds could have reflected enough sunlight to keep the planet cool despite being closer to the sun. This is similar to how clouds on Earth reflect sunlight and cool the surface below them. The key factor would have been Venus's rotation rate. Today, Venus rotates extremely slowly, but it may have rotated faster in the past. Tidal interactions with the Sun could have gradually slowed its rotation over billions of years. A faster rotating Venus would have had different atmospheric circulation patterns, potentially supporting a more Earth-like climate. If Venus did rotate faster early in its history, it might have generated a magnetic field like Earth's. This magnetic field would have protected the atmosphere from the solar wind, helping Venus retain its water much longer. As the rotation slowed and the magnetic field disappeared, Venus would have become more vulnerable to atmospheric loss. The transition from habitable Venus to the hothouse we see today would have been gradual. As the sun brightened and perhaps as Venus's rotation slowed, the planet would have warmed. More water would evaporate into the atmosphere. The greenhouse effect would strengthen. Eventually, the planet would cross a threshold where the oceans could no longer be maintained. This runaway greenhouse effect would have transformed the planet within a few 100 million years. Could life have emerged on early Venus? If the planet remained habitable for billions of years, it seems possible. Life emerged on Earth relatively quickly in geological terms, appearing within the first billion years of the planet's history. If Venus had similar conditions, there's no obvious reason life couldn't have emerged there as well. If life did emerge on Venus, what happened to it? When Venus lost its oceans and became the hothouse world we see today, any surface life would have perished. However, some scientists have speculated about the possibility of life surviving in the clouds. At altitudes around 50 to 60 kilometers above the surface, temperatures and pressures are much more moderate, similar to Earth's surface conditions. Recent controversial observations have suggested the possible detection of phosphine gas in Venus's atmosphere. Phosphine is a gas that on Earth is primarily produced by biological activity or industrial processes. The detection was disputed and remains unconfirmed. Even if phosphine exists in Venus's atmosphere, it could have non-biological explanations. Still, the possibility has renewed interest in the question of life on Venus. Understanding whether Venus was once habitable has implications beyond our solar system. Thousands of planets have been discovered around other stars. Many orbit closer to their stars than Earth orbits the Sun, placing them in what might be a Venus zone rather than a habitable zone. As we look toward the future, Venus continues to fascinate and challenge us. New missions planned for the coming decades promise to answer long-standing questions about our sister planet. Beyond scientific exploration, some visionaries have even contemplated the possibility of one day transforming Venus into a habitable world, though this remains far beyond our current capabilities. The upcoming missions to Venus represent a renaissance in Venus exploration after decades of relative neglect. NASA's Da Vinci mission will probe the atmosphere in unprecedented detail, measuring noble gas isotopes that will help us understand Venus's history. The mission will take the first high-resolution images of the Alpha Regio highlands during its descent, potentially revealing geological features that could indicate past water erosion. Veritas will use advanced radar to create three-dimensional maps of Venus's surface, revealing fine details and topography. It will also map the planet's infrared emissions, searching for heat signatures that would indicate recent or active volcanism. Understanding whether Venus is volcanically active today is crucial for understanding the planet's interior and how it differs from Earth. ESA's Envision mission will carry a suite of instruments to study Venus's surface and subsurface. It will search for changes in the surface over time, look for active geological processes, and study the interaction between the surface and atmosphere. Together, these three missions will provide a comprehensive view of Venus that we've never had before. Some scientists have proposed future missions that would include long-duration balloons floating in Venus's upper atmosphere where conditions are more moderate. These balloons could study the atmosphere for months or years, tracking weather patterns and searching for signs of chemistry that might indicate biological activity. Sample return missions, though extremely challenging, have also been proposed to bring pieces of Venus back to Earth for detailed analysis. Looking even further ahead, some researchers have contemplated the possibility of terraforming Venus, transforming it into a more Earth-like planet. This would be an enormous undertaking requiring technologies we don't currently possess. The basic idea would involve removing most of the carbon dioxide atmosphere and cooling the planet. Some proposals suggest using bacteria engineered to convert carbon dioxide into other forms, or constructing enormous sunshades to cool the planet. Other ideas involve seeding the atmosphere with chemicals that would react with the carbon dioxide, converting it into forms that would rain out onto the surface. Once cooled sufficiently, water could be imported from comets or other sources. Eventually, the thinking goes, Venus could be transformed into a second Earth. However, this remains purely theoretical. The energy required would be immense, and the timescales would span centuries or millennia. More realistic in the near term would be floating cities in Venus's upper atmosphere. At altitudes around 50 kilometers, the atmospheric pressure and temperature are similar to Earth at sea level. The carbon dioxide atmosphere below would provide buoyancy for habitats filled with oxygen and nitrogen, the same way helium balloons float in Earth's atmosphere. Solar panels would provide power, and the atmosphere itself could provide raw materials. Whether humanity will ever establish a presence at Venus remains to be seen. What is certain is that Venus will continue to teach us about planetary evolution, climate change, and the diversity of worlds in our solar system. Venus serves as a cautionary tale about greenhouse effects and shows us how a planet similar to Earth can evolve in dramatically different directions. The study of Venus also informs our search for life beyond our solar system. By understanding what makes a planet habitable or uninhabitable, we can better evaluate the thousands of worlds being discovered around other stars. Venus represents a crucial comparison point, showing us the boundaries of the habitable zone and helping us understand which distant worlds might harbor life. And on that note, our journey through Venus comes to an end. We've explored its hellish surface, traced the loss of its oceans, examined its extreme climate, and looked toward future missions that will reveal even more about this mysterious world. Thank you for joining me on this voyage through the cosmos. Until next time, keep looking up, and remember that the universe is full of wonders waiting to be discovered. This is Atlas Reed, signing off from the Nocturnal Astronomer.